Welcome back, geometry students, and welcome to our next lesson. This lesson falls into a new unit, and this unit is all about logic and reasoning and certain types of things. It's kind of a different direction from math. It's one of the reasons I like geometry so much. All right, our first lesson is titled 3.1, Conditional Statements. And we're going to be making statements about several different things here. First off, we want to see that we have this diagram here for us. This diagram is actually a type of Venn diagram. You may have seen Venn diagrams before. A type of Venn diagram. All right, not that's the main part of the lesson, but it's just what we have here. This Venn diagram illustrates something. Okay, we have a square circle, and then the quadrilateral circle outside. All of our square circle is inside of our quadrilateral circle, which means that there are no squares that are not a quadrilateral. They're all inside. Okay, I can make an absolute statement here and say that all squares are quadrilaterals. All squares are quadrilaterals. That's true for my Venn diagram. Okay? And here comes the meat. All right? We can make conditional statements. Conditional statements are if-then statements. They have an if part and they have a then part. So, taking my absolute statement, the if part is that if a polygon is a square. So I can write that if a polygon is a square, and just know that a polygon is any closed figure with segments for sides. So a circle is not a polygon, by the way. So a polygon is a square, then it is a quadrilateral. I'm going to abbreviate quadrilateral to QUAD for you. All right, there's two parts to a conditional statement. There's the first part. We're going to call that the hypothesis. And the last part, the then part, is called the conclusion. Very similar to what you guys have in science. All right, and then we have ways to abbreviate this even farther and use symbols with that. So that's what our lines with arrows is for. I can abbreviate the hypothesis with a P, and I can abbreviate the conclusion with a Q. So this is read, if P, then Q. All right, next piece is we want to talk about a truth value. And so there's a truth value to this statement. The truth value is whether it is true or false. My statement, if a polygon is a square, then it is a quadrilateral, is true. Okay? In order for it to be a square, that makes it a quadrilateral. Not all conditional statements are true, but this one is. All right? The next kind of statement I can make is a converse. All right? And the converse here in the parentheses there we can write backwards. The converse takes our original statement and makes it backwards. It switches the hypothesis and the conclusion. So that the converse of my statement would then be, if a polygon is a quadrilateral, and again, abbreviating, then it is a square. All right, and this switches both the hypothesis and the conclusion, so my symbols become if Q, then P. And looking at the truth value to this statement, if a polygon is a quadrilateral, does that make it always a square? Well, not necessarily, because I could also have other types of quadrilaterals, like a rectangle or a rhombus. So this part, or this statement, is false. The next type of statement we have is an inverse. The inverse makes the conditional statement negative. Makes it negative. So it negates, the word negates the hypothesis and the conclusion. So I negate it with the word not. All right? And I can make it negative with the word not. So if I say if a polygon is a square, that becomes negative if I say if a polygon is not a square. So if a polygon is not a square, it also negates the conclusion, and then I'll say then it is not a quadrilateral. All right, I can use my symbols then. And I can say, if not P, then not Q, because I'm taking the original statement and just negating it. And the symbol for not is a little squiggly line. It's the tilde. So if not P, then not Q. All right, and let's also take a look at the truth value of this. Is that statement true or false? If a polygon is not a square, is it not a quadrilateral? Well, not always, because again, I can have other types of quadrilaterals. Just because it's not a square doesn't mean it's not a quadrilateral. The last statement I can make is called the contrapositive. The contrapositive is actually a culmination of both the converse and the inverse. So the converse and the inverse together. So what that does is it switches the hypothesis and the conclusion and negates it. So switching that, I'll say if a figure is not a quadrilateral, or if a polygon is not a quadrilateral, then it is not a square. Okay, let's use our symbols then. I can say if it's not, the symbol for that is the squiggly line. So if it's not a quadrilateral, not Q, then it is not a square, so not P. So if not Q, then not P. That's the way we read that. All right, let's take a look at that. Is that true or false? Well, if it's not a quadrilateral, can it be a square still? No. So that actually is true. And then looking over there on the left-hand side underneath contrapositive, it says that a conditional statement and the contrapositive are blank. And we can notice that our conditional statement and contrapositive had the same truth value. They were both true in this case. So we can use another terminology and say they are logically equivalent. They're logically equivalent, which means they have the same truth value. Okay, that can be the same that if my original conditional statement was false, my contrapositive would also be false. All right, and then we have a special statement we can make sometimes. This statement is called the biconditional. Let's break that down a little bit. The prefix bi means two, and then we have conditional, so conditional statements. I have two conditional statements. What happens is I can use the word if and only if. I can only use this when the conditional and its converse are both true. So once I write these out and I notice that my conditional statement and my converse are true, I can make that a biconditional. So here's an example. Congruent angles have the same measure. My original statement would say, if angles are congruent, then they have the same measure. And my converse would say, if angles have the same measure, then they are congruent. So since both of those are true, I can make this a biconditional. Okay, it doesn't use the word if in the beginning, it's got the if in the middle. So my biconditional would say, angles are congruent. Let me use your symbol there. Angles are congruent. And it says if and only if they have the same measure. Okay, so there is our biconditional statement. All right, down here at the bottom is this chart. And what we want you to do is fill out this chart with the statement, perpendicular lines form right angles. Okay, make that a conditional, a converse, the inverse, the contrapositive, and then, if possible, make it the biconditional. I'll give you a hint, it can be the biconditional. Not all statements can, but this one will be. All right, let me give you just this, what it is. I'm going to say it to you, but I will not write it down. You can write it down. The conditional statement becomes, if lines are perpendicular, notice we had to switch perpendicular and lines, the words, to make it make sense. If lines are perpendicular, then they form right angles. Okay, the symbolic form of conditional statements are P arrow Q, and so we would read that, if P, then Q. Okay, you fill out the rest of this chart and bring that to class tomorrow.